so we're in section 13.5.1, and we're going to look at running pairwise post hoc t-tests. This is on page 12. All right, so the author is asking, how might we go about solving any like problem questions that came up during analyzing the clinical trials data set. So given that we've got the three different like arms of the study, the placebo versus anxiety-free, placebo versus joyazepam, and the anxiety-free versus joyazepam. So given that we have three separate pairs of means to compare, so what we could do is we could run three separate t-tests and then see what happens and analyze the results. So if we go into the statistical software, we can do it there. So let's pull up this JASP again. We're already in the ANOVA, but we need to try to do a different analysis. So let's go up here, and now it's let's see. It says that it is easy to do it, but you go into the ANOVA and you select post hoc test options. So it looks like that's down here actually. Post hoc tests. I see it. Excuse me. So if we want to do the post hoc test option, we're gonna go down to that post hoc test area, and then we're going to move the drug variable into the, it says active box, which is this box. So we move drug into the active box. And then this will immediately produce a neat table. So it's loading. Let's take a look. There it is. So this produces a table which shows the pairwise t-test comparisons among the three levels of the drug variable. By default, it will display the results for the Tukey approach, but there are numerous other options. Yeah, I see that. So there's the different corrections. You could do the Tukey, Schuffe, Bonferroni, Halm, and Sadak. Later on, we are going to get into the Bonferroni and the Halm approaches. We're going to move into section 13.5.2, which is called Corrections for Multiple Testing. So in the last section, the author hinted at that there is a particular problem with just running lots and lots of t-tests. The concern is that when running these analyses that we're doing, what we're doing is we're going kind of like on a fishing expedition, right? We're running lots and lots of tests without any theoretical guidance in the hope that some of them come up significant. So this kind of theory-free approach for group differences is referred to as a post hoc analysis. In Latin, post hoc means after this. So let's take a look at our table and the results. So we have page 13, figure 13.4, which is should match what we got in our post hoc tests. So let's take a look. So we have a mean difference of negative 0.767, and then 0.267 and 1.033. We have our SE, our DF, our T values, and then we have our P values for, oh, I see. Right here, we just have the Tukey displayed, which is 0.002, 0.312, and less than 0.001. But we can do what they did in the textbook, and we can add the Bonferroni, and we could add the Helm. And it looks like the Bonferroni is the same as the Tukey at 0.002, and then the next one changes to 0.451, and it looks like they're all less than 0.001. The P Helm is having a P value of 0.001, 0.150, and then less than 0.001. All right, so let's keep going here. Again, that displays in figure 13.4 on page 13. That is the pairwise t-test as post hoc comparisons in the software. And it is okay to run these post hoc analyses, but you need to do it with a lot of caution and a lot of care and strategy. So for instance, in our clinical trials example, we should not simply run every possible independent means t-test, because each individual t-test is designed to have a 5% type 1 error rate, right? At the alpha equals 0.05 level, we would need to run 3 of those tests to make every possible pairwise comparison. So imagine what would happen if our ANOVA involved 10 different groups instead of just 3. And then we decided to run 45 post hoc t-tests to try to find out which ones were significantly different from each other. So you'd expect 2 or 3 of them to come up significant by chance alone. The central organizing principle behind null hypothesis testing, right? So the central organizing principle behind null hypothesis testing is that we would like to control the type 1 error rate. But now that we've been running lots of t-tests all at once in order to determine the source of the ANOVA results, the actual type 1 error rate across this whole family of tests has actually gotten out of control. So this is sometimes referred to as an inflated alpha or a type 1 error rate. The usual solution to this problem is to introduce an adjustment to the p-value, which aims to control the total error rate across the family of tests. So an adjustment of this form, which is usually but not always applied because one is doing post hoc analysis, is referred to as a correction for multiple comparisons. So though it is sometimes referred to as a simultaneous inference, in any case, there are quite a few different ways of doing this adjustment. So we're going to discuss a few of them, but just be aware that there are many, many other methods out there. So again, we already added the Bonferroni corrections and the Helm corrections, but we're moving on and we're going to get into a little bit more about what that means. So we're in section 13.5.3, still on page 13. So the simplest of these adjustments is the Bonferroni correction, and it is very, very simple indeed. Suppose that the post hoc analysis consists of m separate tests, and then you want to ensure that the total probability of making any type 1 errors at all is at most alpha with all tests combined. So then the Bonferroni correction just basically says to multiply your raw p-values by m. So if we let p denote the original p-value, and then we let p subscript j be the corrected value, then the Bonferroni correction will tell us that p equals m times p. And therefore, if you're using the Bonferroni correction, you would reject the null hypothesis if p was less than alpha. The logic behind this correction is pretty straightforward. We're doing m different tests, so if we arrange it so that each has a type 1 error rate of at most alpha divided by m, then the total type 1 error rate across these tests cannot be larger than your alpha level. Seems pretty simple. And so let's see. Let's keep going. Now here's an example from the original paper, and the author in that paper wrote the following. So the method given here is so simple and so general that they are sure it must have been used before this, but they cannot find it, so they're only going to conclude that perhaps it is very much simplicity that has kept statisticians from realizing that it is a very good method in some situations. This comes from Dunn in 1961, pages 52 and 53. So to keep going here, to use the Bonferroni correction in our software, again, you just go under the post hoc tests and you check that box under correction options, and you will see another column added to your ANOVA test results showing the adjusted p-values for the Bonferroni correction, which is shown in figure 13.4. These p-values are adjusted to account for the number of simultaneous tests, so you can compare them directly to your alpha level. Then on page 14 in section 13.5.4, we are going to just briefly talk about the Holm corrections. So although the Bonferroni correction is the simplest adjustment out there, it's not usually the best one to use because it's pretty conservative. So one method that is often used instead is the Holm correction. The idea behind the Holm correction is to pretend that you're doing the test sequentially, and then you want to start with the smallest raw p-value and move into the largest one. So for the J subscript TH, largest of the p-values, the adjustment is either p subscript j equals j times p subscript j, or we also have p subscript j, p subscript equals p subscript j plus 1. There's an example given here that the biggest p-value in the first equation remains unchanged, and the second biggest p-value is doubled. And the third biggest p-value would be tripled, and so on. Or it gives the second equation, whichever one gives you the larger test result for your p-value. This might sound a little bit confusing, so we're going to go through it a little more slowly. So here's essentially what the Holm correction does. So first, you're going to sort out all your p-values from smallest to largest. For the smallest p-value, all you do is multiply it by m, and then you're done. However, for all of the other ones, it's a two-stage process. So for instance, when you move to the second smallest p-value, you must multiply it by m minus 1. So if this produces a number that is bigger than the adjusted p-value that you got last time, then you can keep it. But if it's smaller than the last one, then you copy that last p-value. So to illustrate how this works, we have a table on page 14, and we can consider this table. It shows the calculations of a home correction for a collection of 5 p-values. So you can see the raw p-values, the rank J, the p times J values, and the home p-values. So hopefully that can make it a little bit clearer. And although it's a little harder to calculate if you're doing the calculations by hand, this correction, the home correction, has some really nice properties. It is less conservative and more powerful than the Bonferroni correction. And here's an example. So it has a lower type 2 error rate, which is really good. But counterintuitive as it might seem, it has the same type 1 error rate. So as a consequence, in practice, there's rarely a good reason to use the Bonferroni correction, since it's always outperformed by the slightly more elaborate home correction. Now, one of the downsides of using the home correction is that there is no corresponding confidence interval. So if you ask the software to use this correction, the JASP software, and include a confidence interval for the mean difference, by default it will go and use the Bonferroni correction method when constructing your confidence interval. All right, so let's take a break here, and then we'll come back and we'll do Tukey's HSD test.